This second talk is evolving. It continues to evolve. I just made another slide. I'm going to talk about race differences, race and genetic diversity. And I'm going to talk about how different human populations are and how we should interpret it, or how we might interpret it. This is continuous with the first talk in the sense that it's a reaction to the idea that everybody's the same. We can look around us and know that everyone isn't the same, but nevertheless, methodologically, the idea that human population differences are trivial and insignificant is very well entrenched, very well established, entrenched, at least in North America. And I want to look at the source of that and put some context to it. So this morning, people spoke about a spin, and spin is, what's the word? It's an informal word in English. It's not, it's a slang. But it means the interpretation of data or a fact with some kind of advocacy involved. It means taking data and turning it into propaganda. And many of us are familiar when we talk about race and human differences with what I'll call the Lewontin spin, because of a very famous paper by Richard Lewontin about how small human race differences are from 1972. And then I will contrast this with what I'm calling the Salter counterspin. So there's some numbers and some equations here, but again, don't try to write them down. All of this will be on that website in a few days. Well, our race difference is trivial. Richard Lewontin in 1972 said that the fraction of genetic diversity among world populations was about 1/8. Now, genetic diversity is very simple. It means we take two genes from a population and ask what's the probability that they're different. Or we take two DNA sequences and count the mutational differences, and that number measures genetic diversity. Measures how much different is one gene from another in the population. Now, what this 1/8 means is that if we take any single human population, Lewontin said, say Zulus, for example, within that Zulu population, there's about 7/8 of the total human diversity. So he said the within group diversity was 7/8, and the between group component of diversity was only about 1/8. This paper remains a cornerstone of the ideology that there are no meaningful genetic differences among humans. Lewontin didn't discover this number. Cavalli Sforza had looked at world data a few years before, published exactly the same thing, and thought it was unremarkable. It is, we still get the same number, 10 to 15%, and I'm picking the average of 10 to 15% and saying it's 1/8, which is as good as any other number in that region. It's even true in craniometrics. If you take big collections of skulls, make lots of measurements, use a quantitative genetic model, ask about the ratio of diversity within a population and diversity between, we get exactly the same figure. Well, Lewontin in 78 said essentially 1/8 is a small number, it's trivial and insignificant. That means that there are no real differences among races or human populations. And I suppose, I think 1/8 is a small number, but you may come along and say, no, 1/8 is a big number. We have nothing to argue about because it's just a matter of opinion whether 1/8 is small or big. So I want to put this into context in a couple of different ways and put a different spin on it. I have no argument with any fact, I have no argument with any data. I have an argument with a Lewontin spin, and so I'm going to tell you about the Salter spin. Lewontin pointed out that if there were a disaster and one group repopulated the world, we would only have lost 1/8 of our diversity as a species. He used the example of Zulus. This was a bad example but no one knew in 1972 that African diversity is much higher than diversity in other populations. He could have said Maya. Amerindian diversity is lowest. There's a diversity climb away from Africa, which I'll show you in a moment. But if he'd said Zulu or Maya, then we'd have no argument. Is this loss of 1/8 of our diversity, is it meaningless? Well, when we're going to try to treat things with models, we always look at the extreme cases, so let's look at a very extreme case of a bottleneck. Instead of imagining that all humans except Maya were gone and Maya repopulated the Earth, let's imagine that one human repopulated the Earth. Now, we can't do this. I can't self because I can't make eggs. But imagine that I could self. Imagine that we could create a new generation that was all made by 2 gametes from me. I can't do it. A pine tree could, I suppose. What would the diversity loss be? And the answer is it would be 1/2. And the reasoning is pretty simple. My heterozygosity, my diversity is the same as anyone else's. And if we pick 2 gametes from me and made a new individual, half the time that individual would be a homozygote because they'd be 2 copies of the same thing from me. Half the time it would be a heterozygote, there'd be a diversity loss of exactly 1/2. If a single individual repopulated the Earth. Well, this is all word games, but every textbook in anthropology makes a point. It says most genetic diversity is within populations, which is true enough, but it's spin. Most diversity is within a single person. More than half of human genetic diversity is within Tiger Woods, who is a famous athlete in North America who has multiracial ancestry. So if we take one person, we retain half our diversity. If the Earth is repopulated from a single couple, we lose 1/4 and we keep 3/4 of our diversity. If 2 couples from a random mating population were to repopulate the Earth, the diversity loss would be 1/8. We would retain 7/8 of the population diversity, and therefore the Lewontin bottleneck is equivalent to a bottleneck of 2 couples. That does not seem trivial. Right? I can agree that 1/8 is a small number. On the other hand, if you tell me that a species is reconstituted from 4 people, two couples, is that a severe bottleneck? I think it's severe. This is all the same number. There's no argument about the data. The argument is about the spin. The Lewontin spin is 1/8 is a small number. The Salter spin, the Harpending spin is that two couples are a pretty severe bottleneck. I feel silly in a sense talking about this, but every time I open a textbook, there is this sort of ritualized prose about how all the diversity is within populations. And I want to point out that the meaning of this is subject to variable interpretations. Is this making sense? Am I making? Okay. Yeah, so this is what I just said. Spin versus answers to real questions. And what I've been doing is spinning. Now, I want to talk about inclusive fitness and kin selection, Hamilton's theory of inclusive fitness. There's nothing mysterious about it. It's easy to understand why parental care evolves. Parents and offspring share genes. So from the point of view of genes, parental care is selfish. That's not hard, and we didn't need inclusive fitness theory to understand the evolution of parental care. But William Hamilton formalized this and talked about what's called the inclusive fitness of the social trait, that an individual costly act would be favored if the ratio of the benefit to another individual x to the cost to self is greater than 1/r, where r sub x is the coefficient relationship of self to x. Well, this is just turning common sense into algebra, that I certainly should be willing to sacrifice something for my child because my child shares more genes with me than a random person. I should be willing to sacrifice something for my grandchild, but a little less, because my gene sharing with my grandchild is a little bit lower. And we can take this common sense and turn it into algebra and have fun. And so we're going to have some fun. There's difficulty with Hamilton's original formalism. He wrote in terms of the coefficient of relationship. This is a concept developed by the geneticist Sewell Wright that was supposed originally to be a correlation coefficient. It's not very clearly defined. The theory is simpler and easier when written in terms of what's called kinship coefficients. Now, when we look at the theory, read about it, most applications have been to cases of short pedigree relationships between individuals X and Y. For example, X and Y may be parents and offspring, and we talk about parental care. Or they may be siblings. But there's no reason that the theory should only apply to short pedigree relationships. The important fact or parameter is whether individuals X and Y share more or fewer genes with each other than random members of the population. So if I share a lot of genes with you, then if I'm nice to you, it's helping my own genes. Well, here we go. The coefficient of kinship. Pick a gene from an individual X with population frequency P. Pick a gene from another individual. The probability that the gene picked from Y is identical to that from P is this. So I pick a gene from me, pick a gene from my kid. What's the probability they're the same? Well, it turns out that 1/4 of the time they'll be the same gene. Pick one from me, pick one from my kid. Half the time the one in the kid came from me, half of those are the one we picked from me, so 1/4. with probability 3/4, the probability of identity is just the population frequency. So what's critical is the expected frequency of gene identity, the same gene in somebody else. And we can rearrange it. I don't recommend looking at this stuff. If you're interested, download it and look at the equations and play with them. That's the way you understand this kind of thing. Nobody can look at equations and talk and get anything out of them. It took me years to learn that, years of frantically scribbling in meetings, and completely wasting my time. The point is that kinship measures genetic similarity. So on a random mating population, kinship itself is 1/2. With a child is 1/4. With a grandchild is 1/8. Uncle or aunt is 1/8. And these are familiar from genetics textbooks. Well, if we want to go back to the coefficient relationship, it's the ratio of kinship between two individuals to kinship with self. So we can go back to Hamilton's original equations at any time, but they're very difficult with relationship. All right, now we're going to change topics. Population subdivision induces kinship. If we take two Brits, they share more genes with each other than do a Brit and a Bantu. And we can measure excess gene sharing within populations in exactly the same way we measure excess gene sharing between relatives. So I share more genes with my child than with your child. In the world, I share more genes, with another immigrant German than I do with somebody from Japan. And we can measure these things the same way, put the same metric. Now, the amount of subdivision in a population, it can be measured by the variance of the gene frequency among subdivisions. I'm just going to flip through this. It's meant to be looked at with a pencil, not looked at on the screen. But the variance among populations, just the simple variance of gene frequencies, if we divide by a mean gene frequency times its complement, there is that figure is called FST for historical reasons, but the textbooks are full of it. It's the normalized variance ratio. It's exactly what Lewontin was talking about. Under neutral genetic drift, balanced by migration between populations, all genetic loci should have the same expected value of this so-called FST statistic, and this is the number that is 1/8. This is the number Lewontin and everyone else has found to be 1/8 in humans. Well, more yada yada. Bayes' rule, etc. But here is the punchline. In a subdivided population, if we pick a gene from someone and then pick another gene from the same population, the probability it's the same is this number. If we pick a gene from an individual and then pick a gene from a relative, the probability that it's the same is that number.
We can't see anything.
Pardon?
You're pointing at the screen, we can't see anything.
You're pointing at.
Put your hand up and show us up.
Oh. I'm sorry.
Fine.
It's late. It's late. The day. This is the conditional gene frequency of someone in the same gene, same population. Pick a gene from a Brit, pick another gene from a Brit. That's the probability of identity. This is the probability of identity of a gene picked from a relative whose kinship coefficient is F. Those are exactly the same expression. Exactly the same. FSD is exactly the same as F. This familiar variance ratio statistic that Lewontin and everyone else has talked about is exactly a kinship coefficient. So now we don't have to spin anymore. We can put some context on this number 1/8. That's the point of all this Yodel algebra here that we flip past so fast. Because diversity between populations is similarity within populations. They're exactly the same thing. Two ways of saying the same thing. So here's a population of 50 genes. F equals 1. The populations are absolutely different. There's no similarity between populations. Another way of saying it is that any two individuals within a population are exactly the same. It's an absolute difference. F equals 0 means there's no difference between the populations. An individual from one population is no more similar to another individual within his own population than to another one. Here is the human condition. F equals 1/8. It's not perfect, but in general, individuals are more likely to share genes to be the same in the same population. So these are extreme cases. Those are two different species. These are simply two samples from the same population. There's humanity. There's Lewontin's 1/8. Just to give you a graphical picture of what this looks like. Now, so the original question was, how related in a world context are two Brits? The answer is 1/8. This is exactly the same as kinship between an individual and his grandchild, or an individual and his nephew and his niece. Now, grandparental relationships or uncle-niece relationships are fuel for inclusive fitness. We all understand why we might favor our grandchildren. The Salter spin is that there is exactly the same fuel for ethnic nepotism. That if you walk into Heathrow Airport and that you see somebody who looks like you, your excess gene identity with them is exactly the same as your excess gene identity with your own uncle, or your grandfather, or your grandchild. And this is not trivial. This is not insignificant. Against the Lewontin spin that ethnic and race differences are trivial, this seems to be a lot. There's fuel for selection by inclusive fitness. It's completely plausible that all kinds of ethnic nepotism and racism and everything else could be favored by natural selection. Now, whether it was or not is another issue. We don't know that much about it. Looking around the world, to me, it seems to me that you don't need gene differences to hate people. So in Ireland, they're all the same and they nevertheless kill each other. Middle East, genes aren't very different and very good feelings. So I don't think there's a lot of empirical support for this. On the other hand, there's interesting experimental support that maybe we'll hear some about. Conclusion. Race differences may not be so insignificant for social evolution in our species. And all of the above was absolutely devoid of evidence or ethnographic examples, but I think it is important to understand that they can be spun several ways. But it brings up an interesting question. And here, I think, is a very interesting question for all of us interested in human evolution. Any of us can recognize someone of our own race that we've never seen before. Now, any of us can walk into Heathrow Airport or Nairobi or Narita or Peking, and we can say, that was a European, there's an African, etc. We can do it 100% of the time. We could, I say probably, I think certainly not recognize our own grandchildren that we've never seen before. Yet, the genetic similarities, just looking at neutral genes, are exactly the same. Now things get interesting. What's going on here? I think if I never met my uncle, and I saw him, somebody says, "Is that your uncle?" I'd say, "I don't know, I have no idea." But if I go into Heathrow Airport and somebody says, "Is that a Dutchman?" and I say, "Yeah." It's not, a Bantu-speaking sub-Saharan African every time. Why the difference? And I don't know why, but I can throw out some background information and talk about some ideas. I'm going to do it really fast. Neutral genetic markers. Interesting patterns. There's a diversity decline away from Africa. There's smooth isolation by distance. And what's most interesting is that unusual looking populations do not have unusual neutral marker frequencies. Kalahari Bushmen do not look like their neighbors. They do not look like black Africans at all. If we look at their neutral markers, they're completely generic African. Look just like their neighbors. But in appearance, they don't. All around the Pacific Rim, there are pygmy-type peoples. They look very different from their neighbors. We look at their DNA, it's exactly the same as their neighbors. So here's some real data I decided to break down and show you something real. This is diversity, heterozygosity, a measure from microsatellites, one of those VNTRs I was talking about before, within population genetic diversity. And this is genetic distance from Africa. And there's a smooth decline. The further you get away from Africa, the lower human diversity is. So how different are two Zulus? Well, two Zulus are pretty different from each other. How different are two Chinese? They're less different from each other. And this particular data set doesn't have it, but if we had Maya, if we had Amerindians, they're down here. They're down here. The diversity decline goes all the way into the New World. Apparently, modern humans mostly came out of Africa, and as they moved away, there was a diversity loss. How similar within race our populations to each other? This is a map of genetic similarity. The same populations. Up here are Northern Europeans, French, Poles, Finns, Europeans, all clustered together. They're all like clones of each other. Here are all Asians, Africans again, but notice the old point, the diversity within Africa. African populations are much more different from each other than are these European populations. This looks like three clumps, three races, but if we have intermediate populations, Central Asia, or Ethiopians, or whatever they be in between, the world pattern is smooth isolation by distance. But populations mix. Now, I want to, again, throw out a hypothesis, just for something for you to think about working on. When populations mix, neutral markers blend. We take two populations, one that's all A and one B, and let them mate, and they end up half A and half B. But a lot of other markers that we use as anthropologists probably don't blend. Language doesn't blend. If you allow, say, people from Turkey to migrate to Germany in a trickle, you don't get a language that ends up being a blend of German and Turkish. People either learn German or they don't, but there's not blending. There's a common type advantage. The reason you have to speak the same language someone else does. So selection operates on language in a very different way than it can operate on genes. There's an advantage to be the common type. In genetics, you may remember the RH system operates this way. RH plus is stable, RH minus is stable, mixtures are unstable. You always do better if you're the common type. Darwin said race differences, visible race differences, were caused by sexual selection. And the environmental explanations for human race differences, most of them make very little sense at all. All our books are full of explanations about why white skin is advantageous in cloudy environments. If that were true, the Tasmanians should have turned white. They've been isolated for 10,000 years, way in the South Pacific, where it's colder and more miserable and the worst that Sweden has to offer, and their black is cold. There's lots of these kinds of exceptions. It's an interesting possibility that appearance and how we look is more like language, that it reflects selection for a common type, and that appearance is telling a very different story from these neutral genetic markers. Here's a map of human languages. I'm just putting this up here. This is from Maren Rulin, the major families. I'm just putting this up here to show you that language really has absolutely no relationship to gene differences. Chinese is a member of the yellow language family. Japanese is a member of the green language family. There's no relationship. These are as different as any languages in the world. Genetically, they're exactly the same people. This yellow language family is interesting. It's what's called Nodinae Caucasian. From the Basques, Caucasus Mountains, a group in Siberia, Chinese, and the
Screen, Henry.
Pointing at your laptop.
I'm sorry.
Just you.
I'm accustomed to transparencies where you can point at them. Japanese and Chinese, they have exactly the same genes. The DNA is the same. You can't tell them apart. Their languages are as different as any languages on Earth. This color is so-called Nodinae Caucasian. Basques, Caucasus Mountains, a group in Siberia, Chinese, the Athabascan languages of the New World seem to be related to each other. There's not a trace of this in the DNA. You could look at genes for a year and never see this. It's a completely different pattern. The similarities are local, if any. And I just mentioned something about Kalahari Bushmen. I showed a slide of a few hunters earlier. If we look at their neutral genes, they look exactly like their neighbors. Their genes look like their neighbors, but they're short. They have fairly light skin color. They have epicanthic folds in their eyes, like people from Asia. And they have a so-called mongoloid spot. What this is, if newborn babies have a bluish discoloration in the base of their spine in infants, it doesn't last for long. I have no idea what it's about. It's called the Mongoloid spot because Asian people have it. Every Bushman infant I've ever seen has one. The Europeans, they look like, Cambodians or something. There they are, southern Africa, as far from the rest of humanity as you can get. Their neutral genes are completely African, and they look like they're from Vietnam or Cambodia. 2 Europeans, but you see, maybe this is just European, racism or European, maybe they don't really look like Asians, but let me show you the Bushman view of things. Bushmen divide animals into 3 categories. Ka means meat. It's something you can eat, so a giraffe, a kudu, a hebsbok, these are ka. A coma is an inedible animal, a predator. And coma includes hyena, lions, me, black people. These are all called coma. A Jew means a person. And they call other Bushmen Jew. And Japanese anthropologists, Filipinos are immediately called Jew. The point being that it isn't just me who thinks they look Asian, they think they look Asian too. Now, how do we have this rather complex phenotype, 2 ends of the earth? I doubt that it's an accident. I expect that, the complex, whatever it is, that makes us and Bushmen themselves think they look Asian, that it probably is ancient, but that probably the dynamics of appearance and what we call race may be more like language and sexually selected than like these neutral genes that were the subject of all that 1/8 and 7/8 and that whole dance that we did. So, my conclusion is that, that's my conclusion, that race differences may not be so trivial, and that there's probably a pretty interesting biology to be done with them, and that we haven't done for 100 years. And I think it'd be interesting to get back to it, and thank you very much.
Any questions on the Harpending scheme?
This isn't really a scientific question, it's just one of sort of general interest. If your story is true, why do all the textbooks say different?
Say,
What, if your story is true, why do all the textbooks spin it differently and uniformly?
well, there's a lot of ideology and bad feelings on this earth about human differences and about race in a rather gruesome history. And my own view is that, I want to understand the world. But it's not, a polite, a politically acceptable topic, especially in North America. In Asia, people don't have any trouble with it. I've given talks about this in Japan. Africans don't have any trouble with it. But in North America and Europe, it's something we're not supposed to talk about. So people have grasped onto this Lewontin 72 paper. There's a special on public television in North America all about how wonderful this paper was. Nothing wrong with the paper, but you can spin the same facts different ways, which is what I was showing you.
Surely you're not suggesting that the degree of inbreeding is the same in any European in the human population, are you? Not suggesting that this is a constant.
The degree of
inbreeding.
Well, the only way we can measure inbreeding is genetic diversity, and there's more of it the further you get from Africa. Among large populations. Now, certainly you can find islands and places like that where there's been diversity loss in small populations. But the global pattern is a diversity loss away from Africa all the way into the New World.
But what do you make of those vast mixed populations, like let's say so-called mestizos in Latin America?
Oh, well, any mixture increases diversity. So their diversity is not as great as Europeans, but it's more than Native Americans because of the mixture, sure. Whenever you mix populations, diversity increases, sure. So I'm talking about the Aboriginal New World populations.
What about the Ainu, for example? Where do they fit?
I don't have any data. I don't know. I mean, they've been pretty small. No, I have no data.
They've been described as phenotypically very close to Europeans.
Well, but the Bushman example, I think, shows that, whatever goes on with external appearance, what people look like, doesn't bear much relationship to, the neutral DNA we use to assess history. So it would be interesting to look at their markers. I haven't seen the data.
So you're suggesting that certain very apparent phenotypes are not good guides to genetic relatedness?
Yes, exactly. I mean, I'm suggesting that the DNA is just one kind of marker use. Language is another. Appearance is another. I'm suggesting they have very different dynamics. That they're not all going to tell the same story. That's my suggestion.
We can't hear them.
The main question is why this is a common tradition to use these neutral genes for population genetical studies, not to use specific genes. Because if you are using that portion of genes which is specific, then probably you will find out that there is some population-specific markers. I wonder why all the studies are done on neutral genes, which is obligatory should be universe if they are neutral.
Because I think the honest answer to your question is that the mathematical theory of neutral genes is much simpler. And if we have a simple theory, we want to collect data that applies to the theory. So there's beautiful mathematics about neutral genes. And so everyone was looking for neutral genes. But to be fair, I think it's only since we've been able to look at the detailed molecular history of genes, like I was talking about with different kinds of coalescent trees, that we can identify what's been subject to selection. I think we couldn't identify them very well before. I think now we can. And I think we'll see a revolution in the next 10 years.
Another question, what percentage of our 30,000 genes is multi-allelic?
Oh, it depends on how you split up the DNA. A rule of thumb is this. If I take 2 strands of DNA from this room, just 2 at random, and line them up, there will be a difference about every 1,000 bases. These are called SNPs, single nucleotide polymorphisms. And they occur in a single pair of DNA strands, about 1 per 1,000 DNA bases. So, how many genes are multi-allelic? Well, it depends on how big a chunk of DNA you choose to call a gene. If you take enough DNA, everybody's different. So, all genes are multi-allelic if you choose a big enough chunk.
So I didn't get that.
Oh,
I mean, now that we sequence the human genome, and we know that we have approximately 30,000 genes, surely one can give at least a rough estimate of how many of those loci are multi-allelic.
oh no, not yet. Not yet, we don't know, because, I mean, let's say a gene is, 10,000 bases, and we know it's a gene. Well, if I take a copy from you and a copy from me, there's going to be a few differences somewhere in those 10,000 bases. Those differences may be absolutely insignificant and meaningless. Or they may be physiologically important. We have no way of telling them apart, ordinarily, without a lot of study. But if we take a long enough gene, every single one will be multi-allelic. Every single one will be multi-allelic. But not in a functional sense. It's just that we'll be able to find DNA differences between two copies. Because that always occurs. But see, I think you want to know how often are there physiologically significant differences. And we don't know that. We're just starting with that stuff, I think. Does this make sense? What I just... Students, everybody happy? Makes sense?
Any other questions? Thanks very much.